Okay, welcome everyone to our video on combustion reactions. So in this short video, here are our goals for learning. First of all, I want you to be able to identify the key components, identify the reactants, predict the products of combustion reactions, and then we want to be able to compare the properties of complete versus incomplete combustion. So those are our goals. Now, when we get to combustion reactions, I know everyone gets pretty pumped. It's typically everyone's favorite part of chemistry, seeing things burn and explode. So just a heads up, warning for this video. There are no explosions in the video. We are going to save the demonstrations for live in class. So right now we're just going to be kind of looking at things on paper and being able to recognize these combustion reactions and understand their properties, and then we'll get to see them in the class. Okay, so let's compare oxidation and combustion reactions. Now, the first reaction here, which we learned as a synthesis reaction, where magnesium reacts with oxygen to produce magnesium oxide, is a synthesis reaction, but it's also an oxidation reaction where oxygen reacts with some element or compound. If we look at the second reaction, that is the combustion reaction of butane, where butane reacts with oxygen, producing carbon dioxide and water. So if we compare these two reactions, both reactions require oxygen to proceed. So oxygen is one of the reactants. And the products are oxides. So in the first reaction, we just have one oxide, magnesium oxide. In the second reaction, the fuel which is reacting with oxygen, it has carbon and hydrogen. And so we produce an oxide of carbon, carbon dioxide, and an oxide of hydrogen, H2O, water. If we look at the differences between these two reactions, the way we are going to define combustion is that combustion is a reaction between oxygen gas and a hydrocarbon, which will be any molecule that is mostly made up of hydrogen and carbons. So a lot of the examples we'll look at and the demonstrations you'll see will be just some molecule with some number of hydrogens, some number of carbons. Sometimes you'll see oxygens included in that, and the best example there is the reaction of cellular respiration, where oxygen reacts with glucose, C6H12O6. So it's a hydrocarbon, but it also has oxygens there, and that produces carbon dioxide and water as well. So once again, our definition for combustion reactions, a hydrocarbon reacting with oxygen, which produces carbon dioxide and water. So the way we'll think about combustion is it is a specific type of oxidation. Oxidation is something we'll cover more in later years in chemistry, but oxidation is just any reaction which involves the transfer of electrons or the loss of electrons, and both of these reactions actually involve that. So how do we recognize a combustion reaction? So on paper, when we see the formula, we see a hydrocarbon fuel, and oxygen is the other reactant. Now, technically, there's lots of combustion reactions that involve fuels which may not have carbon in them. So, for example, rocket fuel often contains some nitrogen-based fuels. But for our purposes, we're going to stick with hydrocarbon as a fuel for our definition in this course of combustion. One of the products will always be water, H2O. And if it's complete combustion, it will include CO2, carbon dioxide. So as you probably know, to start a combustion reaction, we need to put in some sort of energy. So we've got the fuel, Maybe it's a propane in a gas barbecue. Maybe it's the natural gas in a gas stove. Maybe it's a piece of wood in a campfire. And that fuel is fairly stable by itself. It doesn't just start to light on fire without any input of energy. And the reason why we need that input of energy is we need to destabilize the bonds in the hydrocarbon. So the energy stretches and breaks some of the bonds, and that allows oxygen to start reacting with the fuel. So even though there's oxygen all around us right now, the oxygen has a hard time reacting unless we start off by breaking some of those hydrocarbon bonds. Once the oxygen gets going, it can proceed through the fuel and start to break up the bond. So, as you probably know, most forms of combustion in our everyday lives are fairly inefficient. They're fairly incomplete, which means we don't break down the hydrocarbon and we're left with some unwanted byproducts. There is one type of combustion which is a specific type, has a specific type of fuel, which is viewed as the most efficient, and that's the combustion of hydrogen. And so this is one of the reasons why hydrogen fuel cells are a large area of research for developing a green and a clean economy, because the reaction or the combustion of hydrogen is very efficient. All it produces is water. But more importantly, which you don't see in the chemical equation, is that is highly energetic. So not only does it only produce water and doesn't produce carbon dioxide or carbon monoxide, greenhouse gases, but it produces a whole lot of energy. So you just get water and energy through this reaction. Okay, so now we're going to compare complete versus incomplete combustion. On this photo that I have out here on the screen, on the left, I have two flames which are undergoing incomplete combustion. On the right, I have two flames which are undergoing complete combustion. So what I want you to think about when we talk about the properties of incomplete versus incomplete combustion, I want you to think of those yellow flames, and the best thing to keep in mind if you're thinking of incomplete combustion is thinking of a typical campfire, okay, that you might have in your backyard or if you go camping. And for complete combustion, you should be thinking of those beautiful blue flames with the three triangles that we want to get when we are using our Bunsen burners there, because they really exemplify the differences. Let's start off by looking at the conditions that are required for a complete combustion reactions and contrast those with an incomplete combustion reactions. As I'm going through these, there's a fair amount of writing, so feel free to pause the slide and copy these points down on your handout before we move to the next slide. So I'll put everything up here because you can see that complete and incomplete combustion are simply opposites. The key here and the key idea is that, one, we need a lot of oxygen, so a high percentage of oxygen in the mixture, and there also needs to be really good mixing of the fuel and oxygen. If you can do that, you'll get complete combustion. If you can't, you'll probably get incomplete combustion. If you have a yellow flame with your Bunsen burner, I'll often tell you to open up the air valve, and that allows more air from the room to mix with the fuel and to get a better flame, a hotter flame, which means more complete combustion. The other thing that you need is good ventilation. If the product gases, carbon dioxide and water, start to build up, then they are going to start being involved in the reaction, and you'll start to get incomplete combustion. Okay, let's look at the products. For complete combustion, simple. Complete combustion produces water and carbon dioxide, totally predictable products. For incomplete combustion, we get a variety of products. And so sometimes we'll get carbon monoxide. Sometimes we'll get some carbon soot. Sometimes we'll get unwanted hydrocarbon byproducts where the fuel has not been totally broken down. The point is, with incomplete combustion, we can't totally predict the products on paper. They will vary. You'll see this in an upcoming example. So combustion of propane, C3H8. Propane plus oxygen produces carbon dioxide and water. So there we have a complete combustion of propane. If this reaction conditions meant the reaction was going to be an incomplete combustion, here's how the products may look. We get carbon dioxide, we get water, we probably get carbon monoxide, CO, we probably get some carbon, which we'd often see as black soot. And then the last product there, CXHY, is my unknown hydrocarbon byproduct, which means we'll get a variety of hydrocarbon chains left over, and the X and Y are just variables saying we don't really know what they will be. And if you'll notice in these two reactions, I was able to balance the first reaction, and I did not balance the second reaction because the products are unknown. So, to summarize some of the general products that we've talked about already, for complete combustions reactions, on paper we can balance them, and that is because the products are known and predictable. A complete combustion reaction has no soot. It is a clean burn. The other property is the reaction is very, very quick. It's highly energetic and quick. For an incomplete combustion, we cannot balance it because the products are variable, unpredictable, and they change over time. The second property is how long the reaction takes. And the way I think about an incomplete combustion is a campfire. That's just a perfect example of an incomplete combustion reaction where the reaction lingers. Okay, it's everything. The reactants take a very long time to break down, and you got a really orange and yellow flame. And then we call any sort of leftover carbon which is produced soot. Finally, let's just look at the energy properties, the energetics of these reactions. In a complete combustion reaction, the hydrocarbon fuel is totally broken down. Energy is stored in those bonds. And so by totally breaking down the fuel, we get the maximum amount of energy out of that hydrocarbon fuel. Whereas in an incomplete combustion reaction, the hydrocarbon fuel is incompletely broken down. There's energy left in those bonds, so the reaction is going to be less energetic. A few side notes here. When you are predicting the products of a chemical reaction on paper or balancing, we will always assume it's going to be complete combustion because you can't balance an incomplete combustion reaction. So take a note of that. And we'll stop there for our video, and we will see some of these examples in class next day when I demonstrate some of these reactions.